So we now have quite a few tests that will tell us if a series will converge or not. And these include the geometric series test, which has this special form of a r to the n. We have the nth term test, which just tells us about divergence, doesn't necessarily tell us if things converge. We got the telescoping series test, which is a pretty special situation. We got an integral test, which says we can take some function and we can take the integral of it. And let's see, we just need to fix a little notation here. It doesn't have to be in this form for the integral test. It's just a general series of a sub n. All right, some function of n. And we write that as a function and take the integral. Then we got the p-series test. That does have a special form of 1 over p to the n. Got the direct comparison, where we look at two sequences and we look at them term by term to see if one is bigger than the other and go from there. And we also have the limit comparison test, where we have these two series or sequences and we compare them term by term to see if their ratio of their terms has a limit. So there's a quick rundown of where we are so far. We got one more type of series called an alternating series. So let's explore that a little bit here. So here we got a series. We got 1 minus a half plus a fourth minus an eighth plus a 16th minus 32nd, so on and so forth. Now, when we look at these types of series, you might notice the first term or one of these terms might be simplified, and you might want to rewrite it to be able to see it a little better. So, this is really 1 over 1, okay? So notice that the bottoms are powers of 2, the denominators. The numerators are just 1. Great, so we got our series, and notice it's alternating because it goes minus, plus, so on and so forth. All right, well, let's look at our partial sums. So our first partial sum, if we're going to just add the first term, well, that is 1. The second partial sum would be 1 minus a half. That would be a half. And if we take that and we add a fourth to it, we'd have 3/4. And if we take that and we subtract 1/8 from it, then we'd have, well, this is 6/8 minus 1/8. So 6/8 minus 1/8 would be 5/8. And then if we add a 16th to that, so this is 10/16, and so we'll add a 16th, that'd be 11/16. Okay, so do you see a pattern here? Well, the denominators again are going 1, 2, 4, 8, 16, and we got 1, 3, 5, 11. Almost looks like this should be 7, huh? But it's not, so watch out. So let's write a summation notation for the series here. Not for the partial sums, for the series. Okay, so this is the sum as n goes from 0 to infinity. And what do we have? We have 1 on the top. We have 2 to the n. But we're alternating. So we've got this fraction. It's positive to start, then it's negative, then it's positive. So we're going to need to multiply this by a -1. And let's think about the power. This first one is -1 to the 0 power, because -1 to the 0 power is +1. This is times -1 to the first power, which would make it negative. So we can just put an n on this here. And what do we notice about the terms a sub n? Well, they are changing signs, or they're alternating signs. Okay, so going back and forth. So do we think the partial sum converges? What do you think? It is shrinking, right? 1/2, 3/4, 5/8, 11/16. Well, it's growing. It shrinks and grows and shrinks and grows. 11/16, remember, is actually bigger than 5/8, because this is really 10/16. So right now we might be thinking maybe. All right, so this is what we call an alternating series, because it's written in this form. Either we have -1 to the n times a sub n, or -1 to the n plus 1 times a sub n. Kind of depends on if we start with positive or negative which form we want to use here. So does a series fit these forms? Yes, it sure does, as we wrote up above there. So if the limit of a sub n is 0, and a sub n plus 1 is less than a sub n, now notice this is the not including the negative 1. Okay, so a sub n would be this part that doesn't include the sign. So if we can say that, then the series does converge. Okay, so this is the alternating series test. So it's alternating in sign, so the sums are going down and then up and then down and then up and then down and then up. Okay, so the partial sums will be going down and up. But if it's true that each of the limit, first of all, is 0 and each of the terms are decreasing, then we can say it does converge. All right, is this true for the series up above? Well, let's find out. Our a sub n is, what do we say, 1 over 2 to the n. Okay, and a sub n plus 1 would be 1 over 2 to the n plus 1. So the question is 1 over 2 to the n plus 1 less than or equal to 1 over 2 to the n? And we might put a question mark there because we're asking ourselves that question. Okay, clean this up here. It's a 2. Okay, is that true? Well, if we multiply both sides by 2 to the n and then multiply both sides by 2 to the n plus 1, in other words, cross multiply, we can rewrite this as 2 to the n is less than or equal to 2 to the n plus 1, and this is true. Okay, so therefore, a sub n plus 1 is less than or equal to a sub n. So this is non-increasing a sub n, the sequence. Does it have a limit of 0? Let's test that out. Is the limit of a sub n equal to 0? Well, let's see. Is the limit of 1 over 2 to the n 0? Yes. So this is going to go to 0 as n goes to infinity. All right? So as n goes to infinity, the exponent, or the denominator, I should say, with the exponent is going to become large, infinitely large, and 1 over that is 0. Okay, so check. All right, and check. So they can say, therefore, the series converges. And this is what we call the alternating series test. Okay, so let's see what that looks like. So the alternating series test says this. It says if a sub n is greater than 0, so we've got a positive. In other words, we've taken that negative out, and we're going to account for that with this negative 1 to the n power, or n plus 1. And so if we just look at the sequence part of it here, okay, if it looks like this, it will converge if it meets these two conditions. Condition number 1 is that the limit of a sub n is 0, again ignoring that negative stuff, and that it is non-increasing. In other words, a sub n plus 1 is less than a sub n for all n. All right? So it doesn't boomerang or come back around or something weird like that. Okay? So let's look at a few examples here. So we know that 1 over n diverges, but what about this? What if we have the series negative 1 to the n plus 1 of 1 over n? Does this converge or diverge? Well, let's write this series out a couple terms. When n is 1, now notice this starts at 1 here. So n is 1, then this is squared, and so we can write this as 1 over 1 positive. And the next one will be negative, because when n is 2, we have 2 plus 1, that's 3. Negative 1 to the third is negative. There's our negative sign. Okay, so when n is 2, this will be 1/2. When n is 3, this will be 3 plus 1, which is 4. Negative 1 to the fourth is positive. So we get 1/3. And then it's going to alternate. Negative 1/4 plus 1/5, ... Okay. So the question is, does this converge or diverge? Well, let's look at these two conditions. Okay. So what's the limit as n goes to infinity of 1 over n? Well, that's clearly 0. And is it true that a sub n plus 1 is less than a sub n? Well, you've got 1 over n plus 1, so that's a sub n plus 1. Is that less than or equal to 1 over n? Question mark. And this is true. If we cross multiply, we have n is less than n plus 1. Okay, and that checks out. So the function, the alternating function, that is, the alternating series, I should say, negative 1 to the n plus 1 over 1 over, or times 1 over n, does converge. So this is the alternating harmonic sequence. Okay, so this is by the alternating series test. Okay, so this is kind of interesting, okay, because 1 over n does not, or diverges, I should say, but if we throw a negative 1, if we make it alternated, this actually does converge, okay? Now notice there's nothing in here about diverging. This is just a test for convergence. So if we want to tell if it diverges, we've got to use something else. So let's look at a couple different ones here. Do these converge or diverge? Well, this is looking alternating because of this negative 1 to the n plus 1. So we can ask ourselves, is it non-increasing? Is n plus 1 over n? Okay, so that's the nth term. So is the n plus 1 term, now we've got to be careful here. What's the n plus 1 term? Well, that's n plus 1 divided by n plus 1. Is that less than or equal to that one? Okay, in other words, are the term by term, is it non-increasing? Well, we can rewrite this as n plus 2 over n plus 1. Is that less than or equal to n plus 1 over n? Well, let's go ahead and cross multiply, and let's see if we can find out. So if we cross multiply, we get n squared plus 2n. And if we multiply n plus 1 times n plus 1, we get n squared plus 2n plus 1. Got to multiply those binomials there. And if we subtract n plus 1, or n squared plus n from both sides, we're going to have 0 is less than, 1. And that is true. Okay? Okay. So it is non-increasing. So this is non-increasing. But what's the limit as n goes to infinity of n plus 1 over n? Is it 0? No, it is not. It's going to infinity. So it's definitely not 0. Okay, so therefore it doesn't pass or doesn't meet the conditions of the alternating series test. Okay. So the alternating series test doesn't help us here, so we have to look for something else. And we have another test that we could use, the ratio test, that will be coming soon, but this will converge. All right, we're not going to prove it right now. I'm sorry, we'll diverge. Let's look at one more here. How about this one? We've got 2 over 1, 1 over 1, 2 over 2, all right, so on and so forth. So does this meet the criteria that that the limit is going to 0. The limit as n goes to infinity of a sub n. So each of these terms going to 0. Yes, that does check. However, notice the terms are not a non-increasing. A sub n plus 1 is not less than or equal to a sub n for all n. Okay, so in other words, you can look here like, how about right here? This term, 2/3, is greater than 1/2. Ignore the negative. 2/3 is bigger than 1/2. Now it's going down. That's 1/3. Well, next one is 2/4, which is bigger than 1/3. So it's not non-increasing. Okay, so the alternating series test does not apply. Okay. And it doesn't apply because it's not non-increasing. Sounds like a double negative, but that's what's going on. Okay, and in fact, this will diverge. So this is actually equal to, and we won't prove it at the moment. You can think about this: 1 to infinity of 1 over n. Okay, which diverges because that is our harmonic series. Okay, so I'll let you look into that. Well, we got a couple of more things here about alternating series. One thing we like to look at is the remainder. So if we take a series and we stop at some point with the partial sums, maybe we don't run that sum out to infinity, we have what's called a remainder. Okay, so we want to figure out how close an actual sum is if we add up in, capital N, terms of an alternating sequence. Okay, so think about this here. All right, so let's think about this proof. So let's say a series does converge. That means it has a sum S, and we take some partial sums S sub n. So we stop at n. All right, so that would give us a remainder. The difference between the actual final sum and where we stopped would be S minus S sub n, all right? So that would be this, the infinite sum minus the partial sum going to n here, all right, would give us kind of the leftovers. That means all of the terms from n up, so the n plus 1 term. And what would be left over would be the n plus 1 term, and then these should all be pluses here. Plus the n plus 2 term, plus the n plus 3, so on and so forth, all right? And then if we factor out negative 1 to the n power from all these, we'll be left with an alternating sequence here of these terms there. And we can rewrite these things to say this is a sub n, and by the way, all these n's should be capital N. Gotta go clean that up. All right. Anyways, so this is going to be the biggest term because remember these are all decreasing, and so we can kind of rewrite this. Notice it's really the same thing if we kind of group these in pairs. And so all of these are little smaller things that are being added and subtracted. All right, and this whole sum is going to be something smaller than a sub n plus 1. All right, so the moral of the story is this: the remainder is less than a sub n plus 1. Sorry for all the typos there. All right, well, anyways, big picture, we get this leftover piece, and the leftover piece is something that is smaller than the next a sub n value, a sub n plus 1, all right? And so this is what we call the alternating series remainder, all right? So if you stop at some value n, then the difference is the remainder, and that's going to be less than a sub n plus 1, all right? And this will be more important down the road, but let's get a feel for it here. So if we want to approximate the error here, so here we have a sequence, and this is a converging sequence. We can use the alternating sequence test series test to prove that. So we have the alternating series of 1 over n factorial. So we have, we're going to stop at 6, all right? So we're stopping here at n equals 6. Well, the actual value is going to be something different. Now, if we add all this up, we get about 6.6319. Now, that is not the actual value of the infinite series here. It's off by a little bit. How much is it off by? Well, we don't know exactly because we don't know the value of this infinite series right now. But we know that the remainder, so that would be remainder r of 6, is going to be less than or equal to a of 7. The next sequence here, or the next term in the sequence. So what is a of 7? Well, that's a 1 over 7 factorial, which is 1 over 5040, which is about 0.000198. All right? So we're really close. We're really close to the actual value. So in many applications, that's good enough for what we need. I mean, this is 1/10,000th here. So that's how we find the remainder. We find the next term, and we know the actual remainder is going to be less than the absolute value of that. All right? Now, by the way, this should be an absolute value here. So it's going to be less than the 7th term.